Okay, let's start. Okay, so this is the ninth week. So first, we will see the eighth week assignment questions, but those are just means if you have read whatever uh, is covered in the problem solving session or in the main lectures, you will be able to do it. It's a simple questions. I don't found I haven't found any numerical questions or something like that. So we'll just slowly discuss and uh, we'll shift to the week 9 context so that the assignment 9, which is pending, you can do it. Okay. So the first thing is assignment 8. Okay. So this is the assignment 8. So the first question asks that if the daytime peak electron density in F2 region of ionosphere was this, some value of electron density is given. So electron density is the number of electrons per unit volume. So that's why it is per meter cube. Okay. During December 2008, what could be the daytime peak electron density in the same region during April 2014? So the thing is that this 2008 means you have to know this that 2008 was a solar minima. Okay, solar minima. That means the solar activity, that is the amount of solar flares coming. So the different different activities like the sunspot cycles and all those things. This is very less active during this period or during 2008. So solar activity is low. Okay. Now this solar minima or maxima, this cycle generally takes about 11 years. It's an 11-year cycle. So when it is at 2008, if it is near solar minima, then as you go, so suppose this is your minima, as you go, the solar activity will slowly start peaking, right? So when your solar activity starts peaking, your electron density starts increasing because from there the plasma and all those things starts or the ionosphere in the ionosphere the ion starts forming. Okay, and because the solar activity is very strong. Okay, so because of that, in 2014, which is 6 years ahead of 2008, you would expect the electron density to increase. Okay. Now, if you look at any of these options, you will find that zero point 0.5, zero point 0.6, and zero point 0.7, they are all less than zero point 0.8 into 10 to the power 11 per meter cube. The only option is D, the fourth one, which is 1.2 into 10 to the power 11. Simple thing is that it will increase. So December 2008 was the solar minimum, but April 2014 will be uh, somewhat higher. The activity will be somewhat higher. Either you do it in this way, or you can see that December is a winter time, whereas April is some way going towards the summer. So you can understand that the solar insolation which is coming at the top of the atmosphere will be stronger. So this is the second approach that April is more close to the summer time, and December is winter time. But the problem of this is that which hemisphere you are talking about. So the thing is that solar activity is playing an important role. Okay, so this is the first one. How are the different layers of ionosphere recognized? Simple, based on their peak electron density. So you might have seen that. Okay, this is the first one. Peak electron density. So something like this. You would have seen that ionosphere. We generally see that where the electron density is peaking. So if it is like this, so this is one of the layers. Okay, having a good peak, local peak. Okay, again here there is a strong peak. So electron density based on the peak electron density, this peak, the layers are recognized. Also, where the slopes are changing. So like this, it is changing the slope. So this is one layer, and this is another layer, like that. Okay. So peak electron density is the right answer. Okay. Let's go to the third one. Which layer or layers of the ionosphere was or were first discovered? So it is E layer. So it's a just not a conceptual question. The E layer. The part of the Earth's atmosphere which is overlapping with ionosphere is effectively neutral. As you can understand, the more the ions are forming, there are processes which we will discuss today called the recombination. That is, in the daytime, when there is a good solar radiation, you will find that the ions starts creating. Okay, but as the solar radiation is cut off during the evening and night hours, recombination, that means the ions which are formed, they combine with electrons. That is called the recombination. They combine with electrons to form a neutral atom. So ultimately, if you take a large volume, you will see that the number of ions and the number of electrons are almost similar. So cancels each other's effect and becomes effectively neutral. Okay. The primary ionization source of Earth's atmosphere, 80 to 200 kilometers near poles in night time during solar maximum, is. So remember, there can be many other options which might be correct, but precipitating auroral electrons is the here it is the particularly the right answer because it has been asked that near poles. So near poles, the auroral electron precipitation is much more important in creating the ionization, particularly at the night time. Okay, so this is so these are all you can understand that if you read those materials, you will easily answer this. There is no conceptual thing here. If the daytime maximum electron density in ionosphere over the globe occurs near Bangalore, okay, then the daytime minimum electron density will occur. Remember, this is daytime, so solar radiation is there. Okay, so in Bangalore, it is close to the tropics. You can understand equator. Bangalore is about 13 degrees north. Okay, now the daytime minimum electron density will happen as you go far away, right? Because the solar radiation, which is falling directly near the tropics, now as you go far away towards the higher latitudes, the solar radiation has slanting rays. So the insolation will slowly decrease, and that is what is being affected, is uh, mentioned here. Okay, so the daytime minimum will be in Russia, which is much more to the northern latitudes. So there, the solar radiation, amount of solar radiation which is coming to the ionosphere will be much lesser compared to that of the near the tropic. Okay. Next, the dominant positive ionic species in F1 and F2 region. So these are also mentioned. It is the O positive ions, and which of the following ion having the major concentration, which contributed of the total electron content above 700 kilometers. So Above 700 kilometers is too far away from the our uh, surface, right? So there you can understand the lighter weight molecules or ions will be much more prominent, right? H plus. Okay. Generally, today also we will see that when we talk about composite F1, F2 layer, there hydrogen and helium based expressions will be there, and you will find that hydrogen comes first, means at the top, then helium, then oxygen. So in that way it goes. Okay. So these are all things which are already been there in the week 8 uh, content. So it is based on those. So nothing very surprising or important. Okay. So so next we will go to the ninth week content. So as we go to the ninth week content, we will again come to the very basics of the atmospheres. That is the atmospheric distribution. So atmospheric distribution is the gas distribution, gas density distribution is what is being asked. So we will use a hydrostatic approximation. Okay. So dpdz will be equal to minus rho into g. Okay. So this is your hydrostatic approximation. We all know this. And we will use another, since we are talking about gas, okay, atmospheric gases, its distribution under hydrostatic. So ideal gas equation is one of the thermodynamic equation which one must use. So ideal gas equation is what it says that P is equal to rho R into T, right? So P can be written as rho. Now this R, if you want, you can keep this R. That is not a big problem because I personally prefer this R to be there. But if you don't want, you can use K by M into T, where K is the Boltzmann constant. Boltzmann. I think Boltzmann has two constant. Okay, and this M is the mean molecular weight or mean mass of molecules. Okay, now what we will do is that, so what I you will see that I have used this, but when we will solve some questions like numerical questions on the scale height, you will find that I will be using this R based things. I'll show you. Okay, so what I will do is that now you have this as the first equation, you have this as the second equation, and so just I will divide it. So dp by p will be minus rho g dz divided by rho k by m into t. Perfect. So now dp by p, rho will cancel, and you will have minus gm divided by kt dz. Right. So finally, if you just do this, so say let's say from p naught to some p, and this is say 0 to some z. So it will be p is equal to p naught. You can understand this is simple exponential expression and minus gm divided by kt into z. Now what I will do is that this part I will write as 1 by h. Okay, gm by kt. So what is h? Kt by km. right? This we call as the scale height. So what is the meaning of scale height? Just by the definition of this, that is where it is that height. Okay, scale height we can define here. So scale height is that height, okay, at which your pressure becomes 1 by E times the surface pressure. Okay. Exactly similar thing we can use for the number density. Say we get the similar expression. So n is equal to n naught e to the power minus z by h. Okay. So number density in case of number density also same, but definition changes that that height at which initial concentration, sorry, the concentration at a particular height becomes 1 by e times the initial concentration at some other height. Okay, so this is also true. Now, for question solving, I would prefer this. See, this R, I will define this R star, which is 8.314 joules per Kelvin per mole. This is universal gas constant. Okay, this is universal gas constant, which we generally use in our chemistry, physics in 11, 12, and all. Okay, but in atmospheric dynamics, we have used RD, like the dry gas constant or something. But remember, for this RD, let's say dry gas constant, okay, what we have said, its value is 287. It's a huge value. But joules per Kelvin per kg. Remember, this is in per kg, but this is per mole. Okay, this is universal gas, but this is the dry air gas. Just remember. So we are using this right now. Generally, R star is actually Boltzmann constant times the Avogadro number. Okay, so as we know that H is equal to kT by mg. So if I just multiply by Na in both numerator and denominator, so what I will get? K into Na is R star T, and m into Na becomes the mean molar mass into G. So it was earlier mean molecular weight, but now it is mean molar or mean molar weight. So it is molecule. Okay. So and this is the mean molar, which you can write it in grams, right? Okay. So this is what you get. This is the final expression of the scale. This is the final expression. Okay. So whenever we will solve some questions, we will use this particular formula. But remember, this is the mean molar mass, which will be in grams, which you can convert it into kg later on and do the things. But in all this, whatever I have derived, one thing is not mentioned. What is that? See, we have assumed here that temperature is constant. So it's kind of an isothermal atmosphere. Okay. So only when there is an isothermal atmosphere, you can see that the pressure decreases exponentially with height. Otherwise, it does not. There is a different expression for that. Okay. But if you look at here to find out the scale height, it is this. Okay. The temperature must be constant. So let us do some numerical questions so that things will be clear. Okay, let's see. Where I have- Yes, let's see. Let us put a question. So you will attend in assignment 9, you find that many questions are there based on this scale height. So calculate the scale height of the hydrogen at temperature of 300 Kelvin. So it has been asked that just calculate for the hydrogen atom. You don't need to worry about any other gas. Okay, just for the hydrogen atom, you calculate the scale height. So for the solution, how will it be? So we know that, okay, we know that for the molar mass, because we will be talking about molar mass now of hydrogen is 1 gram per mole. Okay, this is known. Now the scale height 8, sorry, H, scale height H is, as we have derived, R star by M into G. R star is 8.314 joules per Kelvin per mole, right? Into temperature, it is given 300 Kelvin. What about this? 1 gram per mole, this M, and G is 9.81 meter per second square. Perfect. So let's look at the units. Kelvin, Kelvin cancels. This mole cancels. Other things remains right now. So H becomes 8.314, okay, into 300. This joule, can it be written as kg meter square per second square divided by 1 grams. The grams has to be converted into kg. That is 10 to the power minus 3 kg. And you have 9.81, that is your gravity meter per second. So this second square goes, meter goes, kg goes. So what you get? So it's just simply, okay. So 8.314 into 300 into 10 cube. Can I write 10 to the power minus 3 at the numerator divided by 9.81 meters. Only meter. Alright. So H, the scale height, becomes, so I will multiply with this, 8314 into 300 divided by 9.81 meters. So what it is, if you calculate, it will come up to be 250 meters. So H becomes 254.25 kilometers. So this is the scale height for, if you assume that atmosphere at a constant temperature 300 Kelvin and only hydrogen is there. So in that case, you have, this is the amount, okay, where your hydrogen concentration becomes 1 by E times of the initial one. All right. So this is what you. So this is one of the questions. Okay. Now, so in this way, you try to solve the assignment question. So it is, now it will be easy. Okay. I will recopy that use this expression, R star T divided by mg. Okay. Next is the atmospheric atmospheric density distribution. So if say TMG, we all know what are those are again not a function of Z. Actually, G also varies with height, but very little. Okay. So so let us consider that all these things are not changing with Z. Then your N of Z, that is, this is the concentration of any particular thing, so N naught, which will be at Z naught, or N of Z naught you can write, that is better. So the concentration at some Z naught, initial height, exponential, it becomes Z minus Z naught divided by the scale height. But we can negative this. Same thing. Only thing is that Z naught in our case was zero, and we were talking about the pressure change. Here it is the concentration. Okay, this is the number density. Fine. So this is one of the things. So, couple of things to remember. That is for the mixed atmosphere. Mixed atmosphere means that there are several gases, and we all know that there are several gases in the atmosphere, which includes all the trace gases, the greenhouse gases, and the nitrogen, oxygen, of course, argon, helium, okay, methane, so all those things. So mixed atmosphere, that is less than suppose 100 kilometers. Okay, there's so many things, but major concentration is major. Majorly the gases which are found are N2, which is having almost 78%, and O2, which is having almost about 22%. Other gases are there, so it will be 21 point something, 78 point something. So based on that, other gases will be there. But major concentrations are this. Okay, so in that case, your H will be simply R star T divided by M bar G. So this M bar will be calculated as like this. So 78% of 0.78 into the mass of N2 plus 0.22 into mass of O2 divided by 1, because 0.78 plus 0.22 is 1. So you will find out that M bar generally comes out to be 28.96 grams per mole. Okay. So this is for the mixed atmosphere. But if we go above 100 kilometers, only ionic species, so each species has different scale height, because there is no longer mixture. Now all these N2O2, those have decreased above 100 kilometers. So only couple of molecules are there and couple of gases are there. Each species has its different scale height, right? So in that case, we can write H is equal to either you write KT by small m into G, or H is equal to R star P divided by small m into G. Now this small m, or this m, these are molecular weight, molecular weight. So just so this will be molecular weight of individual. Okay, and this m will be molar mass of individual fluids. Just like we have done for hydrogen. Remember, uh, one thing to remember, this mass, when you are using R star T by mg, this mass will be in grams per mole. But this mass will be in atomic units. Okay. All the values will be same. Okay. So that's the thing. What else? Yes, almost done. Okay. Now we will now go to more detailed discussion of the ionosphere. But I think uh, this scale height, based on scale height, there are two, three questions. So you can now solve those. Okay. Now there is a graph. Okay. So something like this. So this is your altitude, depth, and this is your temperature at Kelvin. So what happens is that this is the neutral temperature. That is, if you combine the entire atmosphere, so the temperature of the environment, you can say, that is your Tn. Now, in the ionosphere, what happens is that this is the temperature of the ions, and for the electron, it is like this. So, thing is that in the ionosphere, okay, so how these observations are made? Very important. People might ask that how these ionospheric observations are made. So, ionospheric observations are made either by satellites, okay, satellites, which consists of uh, several instruments which detects these ions. Second is radar, which is installed at the surface, which may give you some insight of this. And third is the controlled laboratory experiment. Okay. So based on the satellite observations or radar observations, uh, scientists try to do some experiments in their lab and try to model the ionospheric observations. So based on that, these things are calculated. Okay. So so we can distinguish between the ion temperature and electron temperature, the TE. Ion temperature, TI. So what happens is that ions and electron receive thermal energy definitely during photoionization. What is photoionization? That is solar radiation is coming, and one of the frequency. So we know that photons are there, right? So photons having h nu, right? So so quantum photons. So this for a particular wavelength, say extreme ultraviolet, there is a wavelength particular which is means some gases are or some gas molecules or some gas atoms are particularly designed so that it will break itself when it gets a particular wavelength. Okay, so ions and electrons receive thermal energy during photoionization and lose energy, of course, through collision. Next, recombination rate. So, what is this recombination process? We will see those. Okay, recombination rates are smaller, hence, ionosphere, or better to write, hence the ion and electron temperature are above the neutral temperature. Okay, this is we are talking about a height which is greater than 300 kilometers, where the ionic species and electrons are dominant. Okay, so thing is that during the photoionization, it loses some energy. So ions and electrons in the vicinity, you will find more energy and more temperature compared to that of the actual environmental temperature. Actual environmental temperature may be very less. For example, in the mesosphere, or if you go further above, the temperature is generally low. But as you go up, the temperature increases. But near the vicinity of the ions, or so near the vicinity of the ions or electrons, you will find the temperature to be high. Another thing is that this graph also I have shown. So this is how the ionosphere layers can be found. So this is in per meter cube or per centimeter cube, the electron density. So this is suppose the D layer. So you can see that peaks are important. So peak electron density, sorry, peak electron density decides the layer of ions. Okay. Next is, what are the processes which happens in the ionospheric electron or ion production? So this is ionospheric electron or ion production. Okay. So how it happens? Let's see. So there are a couple of processes. The X is some atom or molecule. If it gets a particular frequency or a particular wavelength, okay, photon, what it does is that it forms an ion and it loses an electron. Okay, so this is one of the production process, which is called the photoionization. Using a particular wavelength, remember a particular wavelength. It might be extreme ultraviolet, it will be some ultraviolet, X-rays, whatever. So based on that, a molecule or an atom loses one electron and becomes an ion. Another is the XY, a combination of two things like NO, NO2, whatever. So H nu, it gives you XY plus a similar product, electron. Now, after this, what happens is this XY plus electron becomes XY minus, and X plus electron becomes X minus. So it's not that important, but these are the production processes. Streaming. The several reactions will be there, but what are important, we will just uh, make it. Okay. So this is one of the processes which is called the photoionization, through which the ions are created. That's why during the daytime, when the solar radiation is strong, when these frequencies becomes important, that time only the production happens. Next is different recombination processes. So let's see. So these are the processes which happens in the ionosphere, recombination process. So I will give some examples. There are many other examples in the main lecture. So I will just keep it simple. So this is radiative recombination. Radiative recombination. Simple. Just by photoionization, you have seen that one ion is created and an electron is created. So what will happen is that when the solar radiation is cut off, then this X plus, some X plus, this X can be something. Okay, not always that it will happen. So X plus electron, it will combine with that one electron and give you X and will release one photon. Okay, this is the radiative recombination. But this is a slow process. We will see this. We will calculate something. So this is about 10 to the power minus 12 centimeter cube per second. This is the recombination rate, okay, per second. This many electrons generally uh, recombine, electron or ions, whatever you want to say. Second is dissociative, dissociative recombination. Okay, so this is dissociative recombination where XY plus electron gives you X plus Y. So what is happening is that you have a XY plus, when it combines with an electron, it becomes X plus Y. Means what was combined earlier, now it becomes separated, but the electron is gone. That's the thing. This dissociative one is the fast process, okay, which is around 10 to the power minus 7 centimeter per second. Okay. Third is the charge exchange. So these are several chemical reactions which is happening in the ionosphere. So what is charge exchange process? You will see this is Y Z becomes WX plus YZ. Simply the plus charge which is over this, now it will become over YZ. That's the charge exchange process. This is moderate process. It's not too slow, too fast, about 10 to the power minus 10 centimeter cube per second. And finally, you have the atom ion exchange. Okay, so X plus YZ becomes XY plus Z plus. So what happened? Earlier the plus, the ion was X, but now X and Y will combine and this Z separates out and gets the positive charge. This is atom ion exchange. But this process depends on depends on the chemical bonding of this YZ. Otherwise, how will it separate out and recombine? Okay, so these are a couple of processes. And actual processes, if you want to see of all these things, whether it is the production process or the recombination process, I'll just list down. There are many processes which you can see in the uh, main lectures. So just I will list down. One is the that photoionization. Right? This is what we have started with. Photoionization. This is the production. So simply H nu plus O, so oxygen becomes O plus O electron. Next is what you call as coalitional ionization. This is a very odd process. This is electron plus O. You would expect O minus, but what it happens is that you get O plus and get two electrons. Okay, so this is, I don't know how these processes work, but definitely there must be something in the deep. The deep chemistry is there. Okay. Next is another process called the charge exchange process. Charge exchange process. That is, say suppose hydrogen is there and there is a O positive ion, it just exchanges the charge. That's all. Fourth is called the conversion. Let's see. This is N2 plus O gives you this N and O combines and a plus. This is this is actually the atom ion exchange kind of a thing. Okay. The fifth one is the recombination. This is O plus N2 gives you O2 plus N2. Next is, let's see the radiative recombination, which is very slow process as we have discussed. So radiative recombination, which is O plus electron gives you H nu, a photon, and O. This is a slow process. Seventh, dissociative. This is fast process. So there are many other reactions, recombination. Many other reactions which you can see in the main notes. I'm not going into the details of that. So this is what you okay. So this is the dissociative recombination. Now we will try to see the physical chemistry part of this, and let's see. So for all these reactions, there is a generalized continuity equation. Just like we have the continuity equation for our atmospheric field, here instead of density, we have the number density, dne dt, which is equal to q minus L minus gradient of E. What does this mean? So Q is the production, means somewhere related to the source. Okay. L is loss term, sink. Okay. And what you call it, grad E is somewhere related to the advection. Although there is no velocity here, but this is still advection term, which gives the effects of transport. Okay. Now, if alpha is recombination coefficient, then we can write L is equal to minus D, the concentration of electrons, and dt. Okay. Or I would say that it is, yeah, this is fine. This is equal to minus alpha electron into the D plus. So why am I writing this? So this L is a loss term. And you know, whatever recombination processes we have discussed, these are losing the ions and electrons, right? Finally, you are losing the ions and electrons. So this loss term is particularly based on the recombinations. So that's why we have started with the recombination coefficient. Okay, that is the number of electron concentration decreasing with respect to time. Right? So N is some way related to the recombination process. Because recombination processes are the processes through which the ions and electrons are gone, destroyed. Okay. So alpha is suppose the recombination coefficient. This is the concentration of electron and concentration of ion. Why we are writing this? So if you look at your original reaction of recombination, it is E plus electron gives you P plus H. Right? This is the combination. If you just say radiating recombination process. So this is your recombination process. So the loss can be written as like this. So this is how we write the change in the electron concentration with respect to time. This is the part of the equilibrium, physical chemistry equilibrium. Okay, this we can write. Now, if you assume that the number of electrons lost is exactly equal to the number of positive ions, then we can write this L is equal to minus alpha concentration of electrons. Okay, so this is your lost. Now, one important point that the rate, the rates at which the electron density would disappear will decide the existence of ionospheric layer. This is also true. Why? Because the more the recombination, if the recombination is too fast and there's a large number of recombination, then you can see that the ionospheric layer will fade away because the layers which we have are governed by the peak electron density. Now, if there is no electrons, the peak will decrease, and hence we will find that there is no layer. There is no layer peaking. Okay, so that is what is being trying to say. Okay, now what else we can do? Okay, based on this, the above expression, we can also write that your time constant, we define it. This is the definition. Time constant, say tau, is this alpha E and its inverse. Okay, so it is recombination rate into the concentration and its inverse. As you can see, recombination rate it has per second. So if you just take an inverse, it will be in seconds. So it's a time constant. Okay, so for see for the radiative recombination, we will discuss this later little bit. Radiative recombination, it is about 10 to the power minus 18 per meter cube per second. The volume will remain because it's a number density, you can understand. And second is dissociative recombination. This is not the time constant, this is the alpha. Okay, 10 to the power minus 30 per meter cube per second. This is actually the alpha. Okay, here the alpha. The recombination rate. As you can see, per second, the rate. The time constant is alpha times the electron density and to the power inverse. So in general, what happens is that the electron density, let's say, is almost is about 10 to the power 12. Okay, meter cube. So based on that, we will calculate later on for different reactions that how for different processes, whether one is faster or the other is slow, how will you say that it is really fast or really slow? So we will do that later. Okay, so now let us discuss about a little bit about the different layers like the D layer, E layer, F1 and F2 layers. Okay, little bit of descriptions. A very brief description is being given in the last session, but here we will give some more insights. Okay, so that we will try to see now. So the first is your D layer, the lowermost layer. All right. So, so D layer is generally firm. 50 to 90 kilometers, which we have seen in the last session. How it's produced, very important, how it is produced. So this is produced by the hydrogen Lyman alpha line. Alpha line means this is the alpha means the helium. Helium. Okay. So at 121.5 nanometer. So this particular wavelength is required for the creation of the ions at D layer. Okay. So what happens is that the neutral hydrogen atom, okay, reacts to or is reacts to when, so let me not write this, but so so when electron transits from higher level to that, so higher level is say n is equal to 2, the second energy level state to ground state. Then only this Lyman wavelength will generate. This Lyman wavelength, this Lyman wavelength, when it reacts with neutral hydrogen, it produces ion and helium. So this is how the D layer is formed. So again, this is the lowest region. By the way, one thing is that hydrogen, the major concentration of hydrogen is present at the upper atmosphere. Then at D layer, still hydrogen will still be there at the lowermost layers. So those hydrogen atoms are being targeted by the Lyman frequency uh, photons, and that produces the ions. Okay, so this is the lowest region. D layer is the lowest region, and again you will see that these are weakly ionized as compared to any other layer. So electron density, how much it is? It's about 10 to the power 8 to 10 to the power 10 electrons per meter cube. This is during the daytime. All right, during the daytime. But what happens at night? At night, when there is no solar radiation, actually, there is no solar radiation. The D layer mostly disappears. But near poles or higher latitudes, it still exists. It exists, but it's failed actually. Okay, so I have mentioned the lambda. Yes. Okay, what else? Yeah, that's all. Next is your the second one, which is first discovered layer, which is the E layer. So what are the characteristics of E layer? So first of all, this is 90 to say 140 kilometers. But this also changes whether it is 90. Sometimes it becomes 95. Okay, so it changes. Now see, the E layer is produced by X-ray. and particularly wavelength 1 to 10 nanometers, or and ultraviolet ray, but these are far ultraviolet radiation. So it's about 100 to 150 nanometers. Okay, which ionizes O2 and Na2. Okay, so O2 becomes O2 plus, it becomes N2 plus, couple of other things like the daylight. These are all things which is given in the main lectures. So I've just taken it from that. So daylight maximum electron density is nearly 10 to the power 11 electrons per meter cube. So you can see that the amount of electrons which are produced at E layer is far more, or at least some orders of magnitude higher than that of the D layer, right? And occurs at 100 kilometers, that's fine. And at night, E layer begins to disappear. The reason is same. That is, there is no radiation and things or the ions or the electron tends to recombine. Okay. In between this, there is another thing which is due to incoming metal ion. There is some metal ion like sodium ion, magnesium ion, iron ion. Okay, very thin layer, thin layer and dense layer, thin and dense of electron density can occur in the E region. This is called the sporadic sporadic E layer. What is the meaning of sporadic? Sporadic means actually occurring at few places is generally called the sporadic. Okay. The meaning of sporadic is occurring at few places. But so as you can see, thin and dense layer at a particular uh, height. Okay, so this is the sporadic E layer where the metal ions are present. Okay. What else? After this D and E, we have F1 and F2. So let's write those. So the third one is the F1. So F1 there is from 140 to 200 kilometers. So electron density that I write down is almost about 3 into 10 to the power 11 electrons per meter cube, which is somewhere, I would say, close to the E layer. And this is produced by ionization of atomic oxygen, as you know, because in F1 layer, the oxygen is the major concentration present by the extreme UV. So what is the range of extreme UV? It's 10 to 100 nanometer. So 1 to 10 is X-rays, then comes the extreme UV rays, that is 10 to 100. Further, if you go, that becomes different phases of UV, and then comes the visible. Visible comes from 400 to 700 nanometers. So before that, which is called as a near UV, then middle UV, far UV, or the extreme UV. Okay, so this is couple of points simply, and the fourth one is the F2 layer, which is greater than 200 kilometers and usually has highest the highest electron density, which is around 2 into 10 to the power 12 electrons per meter cube. Okay, this is the highest, as you can see from all others, and primarily consists of ionized atomic oxygen. Okay, and yeah, that's all. Now we will come back to this, what we have done so far. Yeah, we'll come back to this part and try to see what will be the time constant for the two different reactions. So let us say that the recombination process. Some calculations. Okay, we will try to see. So what are those recombination processes? One is the radiative recombination, which we have already seen. This is something like this. So X plus G. This is the radiative one. Okay. And the second one we have done was xy plus electron becomes x plus y. This is the dissociative. We have said that this dissociative is faster than the radiative one. Okay. So let us similarly we write a realistic example of this. So electron is combining with the oxygen gives you O plus H nu. Let us say that the recombination rate is alpha A, and for this electron plus N2 plus gives you N plus N. This is suppose alpha B. Generally, this alpha B, I will just write, it is 10 to the power minus 13 meter cube per second. I think this is per meter. Alpha E is 10 to the power minus 18 per meter cube per second. Okay. Let us say let the electron density is 10 to the power 12 per meter cube. Okay, this is the peak electron density. Okay, the peak electron density. So your TA will be there for what? This will be simply 10 to the power 12, the electron density times the alpha times, which is 10 to the power minus 18 inverse. This is the time constant which we are talking about. This comes out to be 10 to the power 6 seconds, which is roughly around 300 hours. Whereas TB is 10 to the power 12 into 10 to the power minus 30 inverse, which is roughly around 10 seconds. So you can see that dissociative reaction recombination becomes much faster, whereas the radiative recombination takes a huge amount of time. 300 hours means couple of days. Okay, so at night, okay, so at night, so only so if let me write it, if this N2 plus means this one, the for the dissociative one, that is yeah this one. If the N2 plus, if N2 plus is only present, It's only present. Then at night, when solar radiation is cut off, at night, when solar radiation cuts off, okay, then within 10 seconds, within 10 seconds, the entire ionospheric layer will vanish or will disappear. But this is not the case, as you can understand. Only N2 plus is not present. There are many other ions are present, which has which might be, for example, O plus. It's not that in a particular ionospheric layer only N2 plus is present. O plus might be also present. So that will take some time. And once it takes some time, so the ionosphere still exists. More the recombination, more fast the recombination, the layer tend to disappear early. Okay, so this is what one simple example of this radiative versus dissociative recombination process. So recombination processes helps to make the ionospheres dissolve. But since there are many processes, for example, radiative recombination, which takes a huge amount of time to recombine, so that's why the ionosphere still exists during the night. Okay, so yeah, this is done. Next, we will try to focus. Ah, mm-hmm. नहीं 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 ऑल रीजन पे नहीं कुछ अच्छा आप तो वो लैटिट्यूड वाइज बोल रहे हो हाँ नहीं नहीं हर रीजन पे नहीं होगा कुछ रीजन पे रहेगा क्योंकि कहीं कहीं पे ना सोर्स भी रहता है जैसे एज यू गो टुवर्ड्स हाई लैटिट्यूड ना पोल्स की तरफ जाओगे तो प्रेसिपिटेटिंग ऑरल इलेक्ट्रॉन्स कॉस्मिक रेज हाँ उन सब से वो प्रोड्यूस भी होता रहेगा तो कंप्लीटली डिसअपियर नहीं होगा बट कुछ जगह पे जैसे लोअर लैटिट्यूड है इक्वेटोरियल रीजन है वहां सोलर रेडिएशन ही मेन सोर्स होता है तो वहां पे जब कट ऑफ हो जाता है नाइट टाइम पे तो इमीडिएटली वो चाहता है कि वो रिकॉम्बाइन कर ले बट कुछ प्रोसेस स्लो रिकॉम्बिनेशन का होता है कुछ प्रोसेस फास्ट होता है फास्ट रिकॉम्बिनेशन वाले प्रोसेस उसको डिसअपियर करने की तरफ ले जाता है बट जो स्लो रिकॉम्बिनेशन प्रोसेस है वो कंप्लीटली डिसॉल्व होने नहीं देता यही है ओके okay so next so after this recombination is over now we can go for some other processes like which we have discussed like the charge exchange process charge exchange and ion atoms rearrangement. These are other two processes which we have discussed. Okay, so let us take two reactions. One is O plus plus N2 gives you NO plus. Yes, this is one of the things. This is actually the this one, the ions atoms rearrangement. Okay, and let us say that once NO plus is formed, this NO plus will recombine with the electron and gives you N plus O. So this is what? This is a dissociative recombination. So we are talking right now about this ion atom rearrangement recombination. Okay. So this process. So this is the ion atom rearrangement. You can understand O plus plus N2 becomes NO plus plus N. So in the first equation, or first reaction, you can see that there is a production O plus ions plus N2 when it is combining is producing NO plus. Whereas those NO plus which have been produced that now recombines with the electron and becomes neutral. Okay, so that is a recombination. Now, for the first case, so for one, can we write the production rate of ions? The rate of production of ions. Okay, rate of production of ions, which is equal to Kd into O plus into N2. This is how we write, only writing the part. This is the equilibrium concept. Okay, the Kd is the reaction rate coefficient. Okay, so this is what we have. So let's mark it as A. Now for the second one, we are still writing Q. Let me explain. Alpha, NO plus, and electron. Right. See, we are still writing Q. But Q is what? The rate of production of ions. But where is the production of ions here? There is no production of ions. So actually, this Q here is the rate of disappearing, disappearing of electrons. But the rate of disappearance of electron is almost similar to the rate of production of ion. As you can understand, the more this NO plus will be produced, the more it will combine with the electrons and form neutron. So this this rate of production becomes almost similar to the rate of disappearance. But it is also an assumption. It might not be true always, but I would say primarily it is true. So based on that, we can proceed. Okay. So it is actually rate of disappearance, but still we are calling it the rate of production. Okay. So this is your B. Fine. Now, can we write therefore from A and B, can we write therefore that this O plus is Q upon Kd into N2 and your NO plus is Q upon alpha into E. Yes, okay, which we can write. And we know that number of electrons will be exactly equal to the number of ions at a particular volume because effectively it is neutral. So under this, we can write the total electron concentration will be nothing but the total sum of the total ion concentration. Right? So this is, I'm not writing E minus now, let me write E, and this is Q divided by Kd into plus Q divided by alpha times E. Okay. So I will write this into electron concentration plus 1 divided by alpha E square. Okay. Now this can be written as beta H because this nitrogen, as you know, is strongest in the atmosphere, about 78%, as you uh, see near the surface. So as you go up into the atmosphere with this, it actually decreases exponentially with height. Okay, so N2 decreases exponentially with height. So can we write this as some beta of H, which decreases decreases exponentially with height. Okay, so can be called as the loss coefficient. All right, so finally we can write 1 by q on beta H. into electron density plus 1 upon alpha E square. Okay. Now we define some height h is equal to ht called the transition height. Transition height. Actually, it is observed that at certain levels this becomes dominant, at other levels this becomes dominant. Okay. So at this transition height, these two processes becomes almost similar. Okay. Transition height is that height where these two becomes almost equal. Contribution of this and contribution of this becomes equal. So at h say greater than h t above the transition height. So what will happen? Which process becomes dominant? As you know that this beta h, as I have already told you, see, this is the first beta h, this is this. Right. So beta h decreases exponentially. Right? So at higher, say suppose this is h t, at higher level, beta h will decrease faster. If beta h decreases faster, then since it is in the denominator, it becomes very strong. This term becomes very strong. So the contribution to Q will be equal to beta E into electron. On the other hand, at H less than H, other one becomes important. Okay, so this is so there is a transition height when both these terms will contribute equally, but below that the loss of electron term becomes important, and above that this the other term becomes important. Okay. So in both cases, suppose H greater than Hg, you can see that your electron density depends on Q upon beta of H. Okay. So let us draw some figures. Let us say that this is log of Q, the production, and this is height, and this is suppose H naught. This H naught is the height of peak production. Height of peak production. So what is happening? This is it's a peak production and then okay. As you know, in the ionosphere, different layers are found based on that. Right? Now, what happens to the electron density then? So if you have this, okay, only contributed with this condition, then your electron density will become what? So this is supposed to H naught. So you can see that beta H decreases with time, it will be always be higher because if this decreases, Q as it is remaining the same, then this will be somewhat higher. It will be like, okay, it will be higher, just shifting. This is one of the things. Oh, I'm sorry, there is a problem. So beta H, okay, as you know, this is a made wrong. So this is what the beta H is. So initially at the lower levels, it is very strong, right? So Q tends to increase, beta H tends to decrease. So there is an increase here up to the H of the peak. After that, the Q decreases. This see Q decreases. Q decreases. So here what is happening? Q is increasing, beta H is decreasing. So in all ways, it is trying to increase. But after that, here Q is decreasing and beta H is also decreasing. So beta H tends to increase it, but Q tends to decrease. So it will be somewhere like this. So somewhat like this it will happen. Okay, so this is what you get. But if you assume that h is less than h, this kind of a condition where q is equal to alpha e squared. In that case, what will be the electron density? It will be q by alpha root. In this case, it is the clearly simple, which I was drawing earlier. So this is your say h naught. This is your log q, peak production, and the electron density will be shifted to it simply because alpha is a constant. So it's shifted. It's the electron density, and this is the H. The H not remains same. Okay, so these are the couple of things. Okay, what else? Okay, couple of expression. Try to write here. That is, your Q is actually proportional to exponential of minus H divided by H of the tail height of oxygen. Why am I writing it? Because we are now concentrating on F1 and F2 layer or F layer. Okay, so F1 and F2 layer. You know that oxygen is the primary. Oxygen atoms are the primary sources. So the peak production depends on this. All right. On the other hand, beta N, as we know, is depending on the N2 because what we have defined beta is Kd into N2. So exponential minus h divided by the tail height of N2. Okay. Now the electron density is therefore proportional to what? Q by beta h. That is what the expression was. So for this is for h greater than h2 part, it will be h 1 upon h of N2 minus 1 upon h of O. Perfect. This is perfectly alright. We know that h of O divided by h of N2 is about 1.75. You can now calculate based on the expression which I have given. Just check as an exercise. You can just check that how H of O by H of N2 is 1.75. For the oxygen, it is about 16 uh, grams per mole, and for nitrogen, two atoms. So it's a molecule, so 28 grams. So you can see that the ratio is this or not. Okay. Finally, if you solve this, it becomes exponential of h into 0.75 divided by h of. Okay. So you can see that the electron concentration increases with height. Electron concentration increases with height. Right. So this is what showed you. Electron concentration increases. Okay. Now what is okay? And yeah, also there. So you can understand this that I draw two figures. Better if you can go through the main text there. That is much more well visible. So it is just trying to say that if the transition height, if it is greater than the peak production height. So since this is the peak production, so this is your peak production. Okay. That H naught it is producing. Now HT is greater. So this is HT. So will be now. This is your this red dash is your peak production. That is Q. Q. And since HT is greater than the yeah, since HT is greater than H naught, your the electron part is like this and this, right? Because this is your HT. So you know that Q and the beta H will be similar. Or the alpha electron, alpha times electron and beta H times this will be similar. So in this way, in totality, you will get something like this. So this becomes a peak. Okay, so this is the peak of, generally we call this as F1 layer because as you can see, the concentration increases beyond this. So this will become somewhere F2 or something. Okay, this is a very long. Okay, and there are situations you will see that when H is less than H0, you will not find the peak of F1 layer is not visible. This you can refer to the main video lecture or the main lecture. Okay, I'm just giving an idea. What else is there? Yeah, some more important thing. So whatever we have discussed, this these are important points that your this H and H naught, okay, the peak production height and the transition height. This depends on many things. This depends on number one, the solar cycle. Of course, the solar cycle, solar activity, if it is higher or lower, it depends on chi or the zenith angle. What is zenith angle? Zenith angle is, suppose this is your sun, this is your direct radiation, but this is the zenith angle chi. When there is a slanting radiation, zenith ray, with respect to this straight or direct radiation, how much is the deviation of the angle for the slanting radiation? This is the zenith angle. So you know that if you talk about it in a day, so in a day, what will happen? The chi is larger during early morning or dawn, sorry, during early morning or during evening, right? When sun is almost setting or sun is rising, at that time the chi is maximum. That's why you see red color, right? Because the longer wavelength exists. So this is what happens. So more the chi is larger, you will see that your uh, so this, let me write just a bit. Oh, there. Okay. So let's see what else. Yeah. So probability to see if one peak is more during solar minima than okay. So large chi, this electron density is generally small because you can see that the radiation has to travel a longer distance, and that might be the reason for that. Okay, much time, maybe 10 12 minutes we have. So let us do the last couple of things and wrap up. Okay, so next is the hydrogen or helium atoms. How these are playing an important role in the ionosphere. As I have told you that initially at the topmost heights, hydrogen is maximum, then helium comes, and then atomic oxygen and all. So this is with height. Okay. So there are a couple of reactions which goes on. That is H plus H nu becomes H plus plus electron, and H plus O becomes H plus O. So you can see that this is the charge exchange. Earlier we were discussing about the ion atom rearrangement, but this is the charge exchange. Okay, okay. So this H is proportional to, you can see that this is H plus and oxygen, this, right? So can be written H plus, because the ions is what we are interested in, will be H divided by U. Just write the scale height of all these things. And that's all. So it will be exponential minus H divided by H of H, means the scale height of hydrogen, plus plus 5. Why I am writing plus? Because it is in the denominator. H of O. Alright. So generally H of O is 1 by 16 times H of H. So in that way, we can write H plus ion is proportional to somewhere exponential H divided by HO, because it is smaller. So that's why we can write like this. So simple thing is that the concentration of H plus increases with height. So if the concentration is increasing with height, that means what? It is a negative scale height, right? Because what is the scale height? Where we have defined, what we have defined? It is when the concentration decreases to 1 by E. If it is increasing, that means it is having negative scale height. All right. So this is one of the things. What else? So another photochemical reaction. Let me quickly do this. This is the second part. Photochemical reaction. H plus O plus. This is in two-way balance with H plus plus O. They are all chemistry part. So not to worry about. Again, we will be talking about H plus concentration, which will be H O to the power inverse and O plus. So H and O plus is here, so we can write this. And this O inverse, because it's a two-way process, we have to include this. So just write down all the scale height. Okay. And finally, there is an expression like H of O, H of H plus. That's this H plus we are talking about. So H of O plus to H of H. This is always a ratio 1 is to 2 is to 2. Okay, so finally, the most important thing is that final expression is something like this, H divided by 2 of H of O. Again, so hydrogen concentration. With these two processes, we can see that it increases with height. Okay, and wherever the ions are formed, these are called the protonosphere. Okay, and one last thing before completing today's part is the third one, that is helium plus H nu. So this is also in equilibrium. Less than 50 nanometer is the photon wavelength is going to ionize the helium to electron. Okay, and this helium ion combines with an oxygen to give you O plus. This is again the charge exchange process. So we have seen one of the charge exchange processes here, this one, another charge exchange process here. Okay, one is the production process, and there is the charge exchange process. In the earlier cases, we have done ion atom rearrangement and production. Okay, so these are the couple of things. So here also, simply the scale height. Let me write here. Scale height for the helium is 4 times the scale height of the oxygen. So helium is proportional to exponential of 3 divided by 4. So there are many steps in between. I'm not writing them. Just simply this. The main idea is that both both your hydrogen ion concentration and your helium ion concentration increases with height. That means they both have the negative. Yeah. All right. So this is what we are trying to show. So with this, I think today is enough. So let me just go through from the beginning that what we have done today, and then if you have any question, we can. So okay, after discussing the assignment questions, we try to see that how to calculate the scale height of the atmosphere. Of course, with an assumption that your temperature of the atmosphere remains constant. Okay. So what is the scale height? In general, scale height is defined as that height at which the pressure becomes 1 by E times its initial pressure. Means decrease in the pressure. And there are a couple of expressions like KT by Gm, which I prefer is R star T by the molecular mass, the molar mass times G. We have solved the question that how to calculate the scale height. Then the number two density distribution is almost similar as that of the pressure. And then comes the ionospheric part, where you see that the peak electron density regions are defined as the particular layer of the ionosphere. Then, how these ionospheres, in the ionosphere, the electron or ions are produced and how they recombine. So these are the production processes, these are the photochemical processes and others. And then the recombination process. Once the ions are created, how they recombine, because ultimately the total charge. Okay, fine. How they will recombine when the solar radiation or the wavelengths are cut out. So these are the four processes which we have seen. Some examples I have written down. There are many which can be found in the main lectures. And then we try to use the physical chemistry part to understand that how we can write the concentration and expressions. Okay. We have given some insights about D, E, F1 and F2. It is a sporadic layer where the metal ions uh, are present. Then we have seen that a comparison between the radiative recombination, dissociative recombination, where we found that mathematically that dissociative recombination processes are much faster, of the order of 10 seconds compared to that of the 300 hours in case of radiative. Next, the charge exchange and ion atmosphere rearrangements, but mostly we have first concentrated on the ions and atoms rearrangement. First, there is a production and then recombination. So, based on that, we have derived a lot of things, okay, which whose explanation are very well given in the video lectures. We go through that, and these H2 and H naught, which we have defined, the peak production heights and all, this depends on the solar cycle. Chi, the Zen time. More the Zen angle, less will be the electron density, and solar cycle, if it is minimal, the probability that the F1 peak is more is during the solar minima than the maximum. So these are the couple of things. And yeah, so next is the hydrogen and helium ions in the atmosphere, how in the ionosphere it gets produced, and what role does it play. And so we have seen that these H plus and helium ions, they use the charge exchange processes, and we have seen that uh, both hydrogen ions and helium ions, they have negative spin height. Their concentration increases with height. Okay, so this is one of the things. And what else? That's all. Yes, that's all. So I think these are the couple. Now, if you have any questions, you can. Okay. Okay. Sure, we will meet next week then. Okay. Bye.